Hi there! There are so many things to do to build a synthesizer. We need to start from somewhere, right? I thought I would start with a rack, so I can put in there anything I build and start using it. But then I started also working on a VCO, and I wanted to show you where I am with that. And so here you have it, a video on my first tries to make a good VCO. Let's begin! There are several ways to make a VCO, using transistors or op-amps for example, or a combination of them, and there are also ICs that are dedicated to do that. I happen to have a few ICL 8038 in my stash, and so I decided to experiment a little on those first. I can always move to something else if they don't satisfy my needs. Here is the datasheet of the IC. This one comes from Harris. But Harris is not the original designer of the ICL 8038. The device was originally designed by Intersil, but the design and its rights moved to Harris Semiconductors once they acquired Intersil back in 1988. And yes, from this little piece of history you can understand that the ICL 8038 is a very old IC. However, it is still available in the market, and since I have a number of them, I decided to give it a try. If you decide to build a VCO out of it, rest assured that you will be able to find these components in the market. They are old, but not obsolete. From the first page of the datasheet, we can see that this IC is very stable with the temperature, which is a plus. Using discrete components for a VCO implies that we have to do something to prevent frequency drift with the temperature. The ICL 8038 is capable of generating 3 different waves at the same time: square, triangle, and sine wave. As you can see from the block diagram, the actual oscillation is provided by the charge and discharge of a capacitor through a constant current source, which provides directly the triangular shape. The rectangular shape is provided by putting the triangle wave to the input of 2 comparators that drive a flip-flop. The output of the flip-flop is the actual square wave. The sine wave instead is produced directly from the triangular wave through a sine converter, which transforms the triangular wave in the sine wave. The ICL 8038 can be powered with a dual power supply from a minimum of plus-minus 5 volts to a maximum of plus-minus 15 volts, with a current that does not exceed 20 mA. It can also generate frequencies of up to 100 kHz, although we are not going to use frequencies so high. Note also the frequency drift, which does not exceed 250 ppm per degree Celsius. It's a very low value, great for our needs. The output impedance is not great, but that can be easily fixed using op-amps, which we can also use to normalize the output level of the signals, considering that each shape has its own level different from the others. And here is the full schematic of the IC. Also indicated are the needed external components. For example, on pin 10 you can see the external reference capacitor on which the triangular wave is generated. And just on the right of it you can see the 2 comparators for the generation of the square wave, which comes out of the flip-flop on the bottom left. To leave the capacitor undisturbed, the triangular wave is taken from the current generator on the left of the external capacitor, and it is applied to the input of the circuit in the lower center to adjust the output impedance. The same triangular wave is applied to the stage on the right side, with all those transistors in a sort of ladder configuration. And that is the sine wave converter. Those transistors are connected in such a way that they provide a resistance toward ground for the triangular wave, a resistance that changes with the amplitude of the triangular wave itself in order to shape the sine wave out of it. If needed, adjustments to the shape can be done through external resistors added to pin 12 and eventually also pin 1. In this other page we can see the formulas used for the timing and for adjusting the duty cycle of all the wave shapes. And finally, there are examples of a number of circuits that can be created out of this IC, as well as some electric diagrams related to the performance of the device. Today we will go through some test circuits that I made based on the suggestions on the datasheet. We will see what are the features that we can use for our VCO application, as well as determining whether this device is actually good for our needs or not. Here is the first circuit I decided to try. A very basic one, but I wanted to see what the real capabilities of these devices are, to see if it is even worth to make a VCO for the synthesizer. Resistors 4 and 5 are those that control the duty cycle. If the two resistors are identical, we should have a 50% duty cycle. R3 is a pull-up resistor for the output of the flip-flop that provides the square wave. R1 and R2 represent loads for the sine and triangular waves. I won't connect anything low impedance to use these signals, so this should be fine for now. C1 is the reference capacitor and R7 controls the current generator. I previously calculated those values to obtain a range of frequencies covering between 20 and 20,000 Hz. Potentiometer R6 is used to provide a variable voltage to control the VCO, so we can sweep various frequencies for testing purposes. And here is the actual circuit, which I just mounted on a breadboard. This is the ICL 8038, with all around it the components that are part of the circuit. These are the three outputs. The first one on the left is the sine wave, followed by the triangular wave, and finally the square wave. These pins are for ground connections, and this one on top is the positive of the power supply, which will be set to 12 volts. This card here is basically to provide the power supply for the breadboard. I built this one similar to the one I presented in a previous video. It provides dual voltage and ground to the breadboard like the old one, but adds capacitors between each pole and ground, so I don't have to put them on the breadboard individually. So there is an electronic and a ceramic capacitor between the positive and the ground, and there is another pair between the negative and the ground. I also added these two LEDs, each with its own polarization resistor, to indicate if the circuit is being powered or not. So we just needed to plug this little board on the breadboard and then connect its cables to an appropriate power supply. Let's now power up the circuit, and you can see now that the two LEDs are on. Let's connect the oscilloscope now, the ground first and then the actual probe. We start from the sine wave, which we can now see on the screen of the oscilloscope. The wave seems pretty clean, although it seems to have a DC component in it. This should not be a problem, since once we have the impedance adaptation stage, we can also adjust the wave to entirely remove the DC component. Right now, the amplitude seems to be 5.16 volts peak to peak, and the frequency is 239 Hz. Let's now take a look at the triangular wave. This is also a very clean wave, and this one too has a DC component in it. Again, this is something we can remove later with the adaptation stage. This wave has a higher amplitude, 7.68 volts peak to peak, and of course has the same frequencies as the sine wave. And finally, let's look at the square wave. This wave seems pretty clean too, and that too has a DC component, although it seems smaller. The duty cycle seems not exactly 50%, but it is very close, and there are ways to adjust it, which we will examine later. This wave has the highest amplitude, which is basically the one of the power supply itself. No surprise here, since this is the output of a flip-flop. Also the frequency is stable, and the same as the other two waves, as expected. Let's now take a look at the potentiometer. This will allow for changing the voltage on pin 8 of the IC, which is the one that controls the frequency with voltage. Let's see what range of frequencies can we obtain. On the lower part of the range, here I have a 5 Hz frequency. Unfortunately, the duty cycle has now changed dramatically. I hope to be able to correct its change with the frequency later on, otherwise this IC becomes useless for us, really. Let's now go to the other end of the range. It looks like the highest I can go is around 12.6 kHz with the components I've used. Well, this is already very high, and the synth will never be asked to emit such frequencies anyway, but it is nice to know that they can be reached. The duty cycle seems to be okay now. Let me disconnect the oscilloscope now and connect instead an audio amplifier to the VCO output so we can listen to the sound itself and judge it. Here is the workbench amplifier and the loudspeaker that I built some time ago for the lab. You can watch the corresponding videos at the links that are coming up right now here in the corner. The speaker and the amp can easily be connected together like this. I'm going now to connect the amplifier to the sine wave output of the VCO using the BNC connector on the amp side and a couple of alligator clips on the other. The amplifier can be powered up through the same power supply of the circuit under test. For that, I am going to use another couple of cables with banana plugs on the side of the amp, and again alligator clips on the VCO side. The amplifier only needs a single power supply, and so I am connecting it between positive and ground only. Let's now increase the volume and listen. I'm going up and down through the frequencies to have an idea on how the VCO sounds like. You can see how I can reach very high frequencies that are actually disturbing the ears. We are definitely not going to use the VCO at these frequencies. We want to play music, not to torture somebody after all. Here is the second circuit I wanted to test. It is pretty much the same as the previous one, but this time I want to see if I can actually modify the duty cycle of the waves. This is because we may need to adjust it at different frequencies, but also because we may want to forcefully change it to obtain variations in the shape of the waves, to change their timbre, basically. One thing we will certainly do, for example, is to be able to modify the triangular wave to obtain a sawtooth wave, which is very useful to generate certain kind of sounds. So, as I already said, the circuit is similar to the previous one. This time, however, I did not connect resistors R4 and R5 directly to the positive. Instead, I put a potentiometer in between and connected the cursor of the potentiometer to the positive. This way, I can change the behavior of the current generators inside the ICL 8038 and make the charge and discharge cycles different, thus effectively change the duty cycle. Let's see now how this circuit behaves. Here is the modified circuit on the breadboard. This time, instead of having these two resistors directly connected to the positive of the power supply, they are connected to the two ends of this potentiometer, while it is the cursor that is connected to the positive. Moving the cursor in either direction is supposed to change the duty cycle, which will be 50% only when the cursor is centered. Let's now connect the oscilloscope to the square wave output of the VCO, and let's power up the circuit. Here is the square wave on the oscilloscope. As you can see, the shape is practically symmetric right now and has a frequency of 435 Hz. Let's now bring the potentiometer all the way to the left. And this is the effect on the square wave. Notice how the shape is now asymmetrical, and the positive part of it lasts longer than the negative part. And now I am going to turn the potentiometer all the way to the right. And this is the effect on the square wave. This time the shape is still asymmetric, but it is the negative part that is longer than the positive. So, basically, moving the potentiometer allows us to change slightly the duty cycle of the wave. Of course, the 1K potentiometer is small with respect to the 10K fixed resistors. If I had small resistors and a bigger potentiometer, I would be able to manipulate the duty cycle more largely. And now, just for the sake of it, let's center again the potentiometer and connect the audio amplifier, so we can feel the difference caused by the duty cycle on the timbre of the sound. Here is the amplifier and the speaker already connected together. The amplifier input goes again to the output of the VCO and in particular to the square wave output. Let's connect the power cables of the amp to the same source of the circuit, and let's increase the volume and play a little bit with the duty cycle. And now, let's do the same with the triangular wave. Good, and finally let's do it again with the sine wave. Okay, you may actually have noted that along with the timbre it looked like also the frequency changed a little, and in fact it was. The resistors that created the charge and discharge cycles of the capacitor that establishes the frequency range were initially totally separated, but now they have a part in common, which is the potentiometer itself, so part of the charging current flows in the same resistor as the discharging current. And this causes slight alterations of the voltage at the point where the two resistors R4 and R5 are connected together. Basically, it's an interaction, and that causes the frequency to change a little. This is something like we need to keep into account if we want to use the duty cycle variations as a feature of the VCO. Maybe we just need to change the two resistors independently rather than having a single potentiometer, and they have to be changed simultaneously in a way that doesn't change the frequency. I'm thinking on using a switch that selects two different pairs of R4 and R5 resistors, calculated each pair in such a way that the frequency is not changed, although the duty cycle is. We'll come back on this idea on the final version of the VCO, if I decided to use this IC for the project. Let's now see how those two pins, 1 and 12 of which we talked about before, work with respect to the adjustment of the sine wave shape. Sincerely, I'm not sure if we need or not to use those pins in our application of the ICL 8038 as a VCO for the synthesizer. The shape of the sine wave seemed to me good enough already for our purposes, but anyway, let's do an experiment to see if it is worth to add some extra components to the circuit to make it even better. For this experiment, I connected to the circuit two more potentiometers of 100K each. Pot 11 is connected to one side to the minus 12 volts, and to the other side goes to a 10K resistor that goes to the plus 12 volts, and the cursor of this potentiometer goes to pin 12. This way we can control the voltage on pin 12 as required in the datasheet. Similarly, pot 12 is connected to one side of the plus 12 volts, and to the other side to the minus 12 volts through another resistor of 10K. Its cursor goes to pin 1 this time. And here is the assembled circuit, which is the same of the previous experiment, but with the addition of the two potentiometers on the upper left side, along with the resistors in series. The pot on the left provides the voltage to pin 1, and the pot on the right provides the voltage to pin 12. Let's see now how these two potentiometers act on the shape of the sine wave, and see if it is worth to use them to have a better adjustment of the shape. And so let's connect the oscilloscope probe to the output connector for the sine wave and its alligator clip to ground. And let's now power up and let's make sure that the two pots are currently centered. Now let's start playing with the potentiometer on the left and see what happens to the shape of the sine wave. So initially the wave seems to have a pretty good shape if we don't consider the DC component on it. Now I am moving the potentiometer in one direction. It looks like this potentiometer has the effect of changing the shape of the top part of the sine wave, and it tends to flatten it. While doing so, the bottom part becomes more and more pointy. Definitely not anymore a sine wave. If I now move the pot in the other direction, I get back to the original shape, and then I start changing again the shape of the top part, making it pointy this time. Okay, let's put it back now. And now let's try with the other potentiometer. One direction, and then the other. It seems like it acts very similarly to the way the first potentiometer did. I would assume that the capability of adjusting the sine wave shape is there for specific applications that require the best possible shape. I doubt we could hear a timbre difference while working in the audio range, so I don't think I will be using this feature. But of course, these are just preliminary tests, so we will have to see how the final VCO circuit would work once I design it and test it. So, in conclusion, this ICL 8038 seems very promising for using it as a VCO in the Synth project. It seems very easy to use, and it provides good quality shapes, actually 3 of them at the same time. According to the specs, it has also a good stability, and in fact, while testing the IC for long period of times in the lab, I did not see any frequency drift. So I think I will go ahead and build my first VCO using this device. That does not mean that I cannot build more VCOs in the future using a totally different approach. Talking about approaches, what do you think about it? Do you have any suggestions or other tests that I could run on this device? Or maybe do you have other devices that you want me to try? Or a circuit with discrete components? Let me know in the comments. And in the meantime, I will see you in the next video and, as usually, happy experiments!